I cannot, sorry. I try to see the chat at the same time, but
Oh,
it's always
well,
tricky. Oh, perfect. I
how-
think I got it.
okay.
And I got Slack. But please, I don't know, can the people can unmute themselves? Is this possible or
Yeah,
not?
it's not.
Okay.
If they have problems, speak up about it in
Okay.
the Slack.
Yeah, exactly. So don't hesitate to just talk about the Slack or here or whatever. So thank you very much. Today we'll have an introduction to Sycl. I think in the original it was called Sycl Portability. So I have some result, but it's also an introduction. I put gentle because it is the last day and, and one of the last talks. So I guess will be a pretty smooth ride. And at the end, I hope you will understand what Sycl is about and if it is for your core or not. So let's get started of the table of content. So we'll start with a little introduction. Then we'll have a DPC++ with the compiler that we will use. Then a little theory about the context and queue, unified shared memory. And after a quick overview of kernel, how to submit kernel, what is a buffer with already like maybe one of the innovative feature in Sycl, some interop between Sycl and CUDA or OpenCL, and at the end, some performance number. Conclusion and some hands-on at the end, just to show you that it works on Theta GPU, how you want to use it, and all this kind of thing. So yeah, as usual, it is late for everybody. I mean, rough couple of days, so don't hesitate to have any question, either on Slack or here directly. I will be more than happy to have kind of a discussion about all those talk, or just ping me after. So maybe after all this meeting, you heard what kind of programming model you want to use for accelerator. I think you can use this kind of low-level programming model, CUDA, HIP, OpenCL. The problem is like it's maybe not portable. If you work in CUDA, you will be stuck in NVIDIA. HIP makes some effort. Now you have some project to be able to run everywhere. And OpenCL is still targeting to, is still portable, but maybe not some support for a lot of vendors. And it is low level, so a lot of boilerplate. OpenMP, as you saw, everybody like OpenMP. I think you showed nice talk from Colin and everything in the previous day. It is pragma-based. Some people like it, some people don't like it, but it exists. Also, maybe you have heard about Cocos, Raja, or Hoka. We have a lot of things. The major one, or this high-level library-only abstraction layer. I think Cocos is the most popular. And so I think you get some talk by some nice people in Cocos. And then you have Sycl. And so Sycl is a little bit like Cocos. You will see it's really C++, but it is maybe less, how can I say that, less academic and more industry. And we have learned a lot of things from the Cocos ecosystem, from the parallel STL ecosystem. So maybe Sycl, we'll talk a little about, is really by the to explore ideas that will be put in, we hope, in C++, I don't know, 48 or something like that. And at the end, you have parallel STL also if you want to do. I think we have an implementation of parallel STL with Sycl, and I think NVIDIA is pushing a lot with parallel STL. So whatever it is, your choice. So here we'll talk about Sycl with like, yeah, the industry, let's say, C++ C. So what is Sycl? It's a release for C++. So if you don't like C++, you will not like Sycl. If you like C++, you may like Sycl. So, and it is a pure C++. So no language extension, no pragma, no less attributes. It is by the same group that develop OpenCL. So at the beginning, conceptually is borrow a lot of concept from OpenCL. Platform, device, workgroup, branch. So we have reused in Sycl a lot of this battle-tested concept. Sycl source, and I think the thing I like is either implicit or explicit data transfer. So explicit is as usual doing your mem copy, where implicit is where you use buffer, and we'll talk about that later. I like it. And as I say previously, Sycl is a specification where it is by the Kronos group. Kronos is the one who are doing OpenCL, SpearV, Vulkan, OpenGL, and it is public. You can join Sycl and join the committee cool and everything. And you have, since the last revision of Sycl, we have a nice interoperability with other programming model. So it really make porting your code easier, or if you find something lacking in Sycl, you can always go back to your native programming model. So it's pretty nice. And the current stable is Sycl 2020. So in this talk, if I say Sycl, I mean Sycl 2020. Do we have any other question? Let me see. Perfect. So Sycl implementation, we have multiple implementation. As I say, Sycl is a specification, like OpenMP is a specification. So we have a multiple of people, vendors, university implemented. Here are the big three. We have HIP Sycl, Compute CPP, and DPC++. And DPC++ is public and it is by Intel. I have some slide to explaining. And maybe here, what I just want to say is that if you have multiple backend, you can target AMD GPU, Intel GPUs, NVIDIA GPUs with Intel. Same for CodePlay. You can target CodePlay are more for embedded car stuff. So you have already air car, power VR, all this kind of thing. And HipSycl is the academia when you can target some CPUs and some stuff. So a lot of various ecosystem. So that means it is portable, right? It is not something you do and you will work on in one vendor and everything. It's already a little portable. So what is DPC++? I show you, and it's a little confusing because of marketing reason. But so DPC++ is three things. It's the Intel implementation of Sycl. So that means Intel have a Sycl implementation, and they may have some extensions, this kind of thing. But yeah, it's called DPC++. It's also the name of the compiler, who is just a thin layer around their open source compiler with package with Intel One API SDK. So you may have heard about this Intel One API, with the collection where they put all their compiler, ICPX, OneMKL, and all this kind of thing. And inside you will find DPC++, and with also a compiler, but it's just a thin layer around this thing, Intel Sycl, with a fork of LLVM who have all this Sycl stuff, right? So Intel forked LLVM and they implement Sycl in this compiler. And this is the one we will use. So in the hands-on at the end, we'll use Clang++, but it is the Clang associated with the fork of Intel and who support Sycl. Intel have some plan to upstream their fork to the main LLVM, but it is a work in progress. So yeah, so in short, when I will say DPC++, what I mean here, it's Intel LLVM, so it is a LLVM compiler who implement Sycl. Yeah, it's confusing, but nothing I can do about it. So how you want to install, if you want to try on your own laptop, I know a lot of people are doing development on their own laptop because you can run on the CPU via Intel TBB, or a lot of people have some CUDA or whatever, so you can just install it. The easiest is to install some source, or you can use one API and apt-get, or my favorite is just to ask nicely your sysadmin and they will do it for you. I think it is the easiest. So this is DPC++ One API ecosystem. I want to show you. I think here is just to show you that One API is more than just a compiler, right? Sycl is really more than just Sycl. It's really about a lot of other tools around, because if you just have a programming model, you will not go far in HPC. You need everything. So the first thing is a lot of people have already some code. Most of them are in CUDA. So Intel provides some Cyclomatic, who is a translator from Sycl, from CUDA to Sycl, sorry. So it takes your CUDA code and generates some Sycl code. It's used, I know, by a few apps, I am aware, and they were pretty happy with it. It doesn't give you really super nice Sycl as all of the automatic stuff, but it really allows you to port, like, I don't know, if you have 100,000 of kernel, you can just run that, and at the end, you have something good enough to start, and after you can review and everything. And it's worked pretty well, so please try it to get an idea. So that means you don't need to port manually if you are not feeling, but you can also port manually one by one, thanks to the interoperability, if you prefer. So I put the link here, but Synclomatic. 1MKL. So Intel is really famous for MKL, right? I think everybody like MKL. And they did the 1MKL, so it's just MKL, but with some Sycl API. So you can use this 1MKL to be able to run BLAS, LAPACK stuff on the CPU or on the GPU. And maybe the good thing is, like, we have backend for 1MKL for all the vendors I show you, for AMD, for NVIDIA. So it's really nice. So that means you can use 1MKL kind of a portability layer for your application, right? I know every application have an abstraction layer over cuBLAS and all this kind of thing. So you can think of 1MKL as something where ratify standard, and you can use, for example, some applications are using OpenMP, but then from OpenMP they are creating with the interop some Sycl stuff, and after they use 1MKL to be able to target a different vendor with BLAS and this kind of thing. Sadly, we didn't have time to install it on Theta GPUs, but we will do it soon when we find the bandwidth to do so. So please, the spec is open source, and they have nice things. They have like, how can I say, gem, but with batch based gem, and they have FFTs and all this good thing. 1DPL also. So this one is to implement parallel STL and this kind of thing. So if you are really into pure C++, you may be interested by that. And it is also like a parallel STL. So you can try. Do we have any question about this quick overview on the Intel, the compiler and stuff? Okay. If not, we'll continue on a little more about some theory. If you did some CS study, sorry, maybe I have some flashback and some PTSD. It is a UML diagram from OpenCL, and I like it. I will not go really into detail about it. It's just to give you in one picture some concept. As I told you before, Sycl is reusing some OpenCL concept, so I think it's important to understand. So maybe the most important is you have a platform, and the platform have multiple devices into it. From some devices, you can create a context. So the context is something to handle memory. All right, the memory is only valid in this context, so you cannot read memory from other context. And with a device and a context, you can create a queue. So a queue is targeting one particular devices. For now, we have some possible extension, so a queue can target multiple devices, but this opens a lot of problem about performance. And from this command queue, you can get event from this queue. This queue will produce some event, and you can use this event to do some synchronization and all this kind of thing. So yeah, so platform, device, context, queue. And a program, this one, this doesn't really matter. It's just a kernel, but I will show it will use lambdas. So context and queues, as I told before, a platform, it's a collection of device. So here you see I create a platform and I say, I want a platform, give me a platform, but in this platform, I want to have a GPUs. So you can do that, platform. Then from this platform, you can get only the devices. And you say, okay, just give me all these devices, because who knows, maybe you have a platform where inside this platform you have different things, but to be extra cautious, we are saying, okay, we just want the GPU, and I take the first one. And from this device, I create a context, and from this context, I create a queue. From this context and a device, I create a queue. So this is really the verbose way of creating a queue, of creating a stream. Also, you can just, maybe I don't remember correctly in the next slide, but you can just do Sycl queues, only Sycl queues, and it will do that implicitly for you. They will take a device and they will create a context and everything for you. So this one is really the explicit way if you want to have the full control. Oh, I say exactly here. So here, it is what they say, the explicit, where you create the platform, the device, the context. And here it is the implicit way, where you just create a queue. And from the queue, after you can get the device associated to the queue and the context, so you can go up, where here you are kind of a top-down and bottom-up approach. Maybe the problem is this one is like if you create two queues, they will be in two contexts different, right? Because here you create an implicit context. So you need to be careful. We have some work open to create like a default context will be shared by all the queue, but it's still maybe problematic or maybe too much implicit. So we are eager to get any feedback in the Sycl committee about it. Maybe a big difference between CUDA and here, it's a queue are out of order by default. Okay, so they are not a FIFO queue. In CUDA, stream are in order, so you put stuff in the stream, and if you put A and then B, you know that A will be executing, finishing, and after B. Here, if you just issue two commands, A and B into queue, you don't know in which order they will be executed. Because they are out of order, the scheduler can do whatever they want. They can maximize occupancy, concurrency, all this kind of thing. But if you want, you can create a property list and create it in order. So it is possible. So I know a lot of people who port their code from CUDA. They like to get, they were trained, and some in-order queue may have some, it's easier to use, so they are just creating in-order queues. And no problem with that, it is supported. And the smart people already realize if a queue can give you an event, that means the queue submission are asynchronous. So by default, everything is asynchronous in Sycl. So you can say, if something have a queue, take a queue, it will give you an event, and it is asynchronous. So that means when you do a submission, if you want to wait, you will need to explicitly wait for it. Okay, unify shared memory now. So I told you this queue thing, so how to use queue. And one thing people like to do, I don't know why, is to allocate memory. So we have three types of memory. Is pretty, you will not be deconcerted, it's a traditional thing. So host, malloc host, use pin memory, malloc device will allocate some memory on the device, and shared will allocate shared memory. And the API is just you allocate, like we showed before, a memory is bound to a context and live in one particular devices. And so that means it is bound to a queue. So you can use a queue to create a device, to allocate memory. And we'll show that later. So nothing special. Exactly here an example. So I create a queue. I say I want a GPU, just because I'm paranoid and I don't know what the runtime will choose for me. By default, everywhere is a GPU, but I don't know. Let's say I want to be super portable and my code only want to use on GPU. So I pass a GPUs, and then I just malloc device. You see, you have a nice overload. Because I say the type, I can just put n, and I don't need to put a size of float. So regular templating, C++ templating to get a little more convenient in compared to C or this kind of thing. And I get a float here. I can put auto because it will return me a float pointer. Perfect. I have memory, so now I want to use my memory. I want to do some submission, memory submission. And this is here, if you are not familiar for C++, you are a little sad. And if you like C++, you will find this slide totally normal. Now you need to use those lambdas, this little bracket here. And so parallel for can take a lambda, and you just execute the lambda. And in the first argument, you can say, you know, the number of iteration you want to do. And here I have a little nice example where with some std accumulate just to show that I know C++. So yeah, so just q.parallel for, and as I said before, this thing is asynchronous, and this thing return an event. So, and I can wait for the event returned by this guy to finish. So this is why I do q_parallel for.wait, and I know when I will do my accumulate, this function have finished. So always be careful with synchronization, or use buffer as we will see later. We have two synchronous, as a lot of programming models, like exactly like in Cocos and everything. You can choose if you want to do this just range, where you say, this is my global work size. I just want to execute on this global work size, so the total size, and I don't care how the runtime will split that into teams or wrap or whatever it is called in CUDA. But sometimes you want to have more control. This is the first thing you do if you want to have a performance on one hardware. You may lose any portability because you are hard-coding some of the thing, but if the runtime is bad, it hallows your performance. So you can pass the global work size and the local work size. So one is not in CUDA where you say, you say the work group and after, or the block and the number of block. Here you say the global work size and the local work size. So you need to divide one of the two. The two need to be a multiple. So yeah, it is the same in OpenCL. So it comes from OpenCL, this global work and local work. So if you start Sycl, it is something you maybe find confusing because you are, it's different than CUDA. You say the total and after the size of the chunk, where in CUDA you say the size of the chunks and how many chunks you want. Doesn't change that much, but it is a way. And here if you never do how the same code in OpenMP look like that, team distribute are from the group and after parallel for. So you have some control about the teams. Any question? Don't see anything in the chat. And nobody on Slack. So let me continue with buffer, something I really like. Maybe verbose to use, but I think the advantage are really, really useful. It's disable a lot of possible bugs and should enable also far more performance, may give you far more performance. So as we showed before, it's all this dependency problem, right? You need to put weight, but if you put too much weight, that sucks because you have nothing. So you say, okay, I can use in order, but if you use in order, everything we put in your in order queue, you cannot have parallelism. So in order are good, but you may give it some parallelism. So how the standard way is to create multiple stream, multiple queue, and yet you put stuff inside these two queues. It works, but after you may have too much synchronization or how to synchronize. You still need to synchronize between the two things and everything. Out of order queue is good, but you don't have any. You need to handle all this dependency, and it's really tedious because if you screw up once, you will have race condition in your code, and it can be pretty bad. The solution is to use buffer, and buffer is kind of the best of the both world, but it will give you a little. It's not perfect, right? Because it will be a little more verbose, but it is worth it, I think. So I think buffer are like. Okay, I'm not a Cocos expert, so I will not say anything about Cocos, but it may be similar to Cocos View or something like that, but maybe not. It's a little more than that. So a buffer, it's a encapsulate your data, right? So from you have some data and you create a buffer on top of your data. An accessor will describe how you access those data. You say, okay, I will have a read-only accessor. I will have a read and write accessor. And because you tell to the runtime, you tell to the compiler how you will access those data, they can schedule everything, right? For example, if you have to read on the same data, they know that they can execute things in parallel because it's just a read. You can always read in parallel. If you write, in this case, you need to follow in which order they were submitted. And the nice thing is follow C++, the destruction of the buffer will cause synchronization. So at the end, when you go out of the scope, you can just use buffer and everything will be fine. So this is the buffer example just to see that it will not perform any host to device data transfer. So this code just, I have a vector of int on the GPU. I create a buffer. And when I submit, I create an accessor inside my command group handler, and I say it is a write only and no init. That means it is a write only where I don't need to copy back the data. I don't care about what is the original data in buffer A because I will overwrite everything. So please, runtime, don't do any data transfer from the host to the device because you don't need it. I give you the promise that I don't care about the original data. And then I go a parallel for using this accessor. So I just initialize my parallel for. And then I quit this scope. So at the end of this scope, the buffer will be out of scope. So that means I have a synchronization. So I know at the end here, I know that A will be synchronized and I got the values. If you trace this code, you will see that you have no host to device data transfer. If you want to do that using USM, it's more complicated. You can use shared memory, but now you hope that shared memory will be allocating only on the device. So maybe you can do some prefetching. It's not tricky, it's not obvious. Or you have the far more verbose when you device memory and after you do a mem copy, an explicit mem copy. This is the best way, but it's a little, you need to handle your mem copy and you need to handle your dependencies. So either you put it in an in-order queue and you just do this submit and after you use the mem copy, or you put an out of queue and you use the event of this kernel submission to put it on the mem copy to say that the mem copy need to wait. Can I declare a non-const size buffer? Yes, of course, yes. Everything here I can read for argv, you have no problem. The buffer are just, nothing is static. You can just, I don't think you can resize them. I'm not sure, I don't, but you can just non-const totally work. So yeah, it worked nicely. And yeah, the good thing is like the runtime, if you have no bug in the compiler, the runtime should be optimal. So I mean, you cannot do, it will not add any overhead, right? Maybe it's too magic for you because you put a lot of faith on the runtime, but I think this kind of optimization are pretty trivial to do when you are runtime to avoid data transfer to do the correct synchronization, because indeed you did everything. You give all the information for the runtime. It's a little more work because in every kernel you need to put your accessor, but it's pretty nice. And if you come for Fortran, you are used to put in, out everywhere. So it's maybe not a big ask for a Fortran programmer who come to C++. I got a question, how to capture this pointer in the kernel function. We can discuss in the hands-on a little more if we have time. Yeah, so I think the best is maybe to use a functor where you pass a functor, or not. Yeah, you will need, I think, to capture everything by hand. You need to pass everything by hand to access only the mounder function, because it need to be trivially copyable and all this kind of thing. So it depends of this, but we can discuss. Yeah, so maybe in buffer search, at the beginning of time, they were C programmer, and in C programmer, we say, okay, it's easy. I just do alloc and free, super easy to manage. After we realized it was hard, so we say in C++ we use constructor destructor, right? Alloc free is too hard for my little brain. I make always mistake. I have double free. It's difficult. And after in CUDA and in other programming model, we say, oh, dependency is easy. You just need to do the mem copy and the weight yourself. Okay. In reality, it's super hard. We saw a lot of bugs, a lot of poor performance because of too much synchronization. I think in Sycl we have a Sycl buffer, and it's maybe one of the good solutions. Maybe not perfect, but a really good step in the solution. Interoperabilities. Yeah, I think we just have a lot of nice talks in iWocal with the international workshop. I don't know for OpenCL and Sycl. We have SyclCon at the same time. You can check this talk. It was done in collaboration with Intel and with other people from CodePlay and everything. And you can either create an object from a backend, from CUDA, you can create a Sycl object. For a queue stream, you can create a Sycl queue. For a stream, a Sycl queue. The opposite, you can, from a Sycl queue, you can back the stream. Or you can do, I submit a kernel, I take my event, and after I will submit a CUDA kernel, and I want them to be interop. We call it host task. So this is the thing to do. My old PhD advisors always say, I don't care about everything, just show me number, and with number I will. I don't need anything else, so I will show you some number. As usual, some Canva. The data was provided by CodePlay, so thank you very much, CodePlay. We work with CodePlay to develop the A100, the backend for Sycl, for DPC++. As usual, takes all of those by grain of salt. They are metric only on this particular hardware with this particular version. And so, as usual, please measure by yourself. It is the best thing to do. Just take it and bench. And if the performance are poor, just open an issue in Intel LLVM. And if it is in Intel hardware, just ping me because it is my job to make it better. So Babel stream. So Babel stream is just stream. You know, you have copy, triad, and everything. So we expect everything to be fine because they are just memory bound, not the hardest thing to do. And indeed, you see in blue is CUDA, and in the one it's Sycl. And we have also heap and on MI100. And you see everything is fine, right? A little percentage, but who cares? I mean, here we have a problem for dot product, and I think it is solved on new version. But overall, good performance on stream. I mean, portable performance on stream. Lulesh with a mini app, you see it doesn't start at 0, and the higher the better. And you see CUDA is higher, but a few percent only for compared to Sycl. And for AMD, for whatever reason, it is the opposite. The heap is slower than the MI100 Sycl backend. It is, don't over-analyze this kind of thing. I think here it doesn't start to 0, so just to say it is globally portable. RSBench, who is doing some open Monte Carlo thing, You see same similar performance, only a few percentage between CUDA and the Sycl, and same in MI100. Same D/slash with another mini app, and you see here Sycl is faster than CUDA by a few percentage, I don't know, and save Sycl MI100. So I think the conclusion here of this little data is just it's importable for those kind of mini app. Sometimes it's faster, sometimes is slower. In theory, I don't think Sycl should add any too much overhead. If you have a difference, it's maybe just due to a bug and we can fix it, but I don't see any fundamental reason that those kind of things add any overhead for the compiler or this kind of thing. So maybe for kernel code, you like some features, some access to local memory, shared memory, and everything. Maybe CUDA give you more flexibility, but Sycl give already a lot of flexibility. You can use subgroup, intrinsic. You can even use assembly in your kernel if you want. So I don't see any. So if some intrinsic you are using are not yet available, just tell us, and we can work with CodePlay to implement it. So for better or worse, Sycl is C++. So a lot of C++. Many vendor, many hardware are supported. I'll show you Intel. I didn't show you Intel because of NDA reason, but trust me, maybe it worked. So we have Intel, NVIDIA, AMD, lot of hardware, CPU, GPU. For the crazy who like to wait 20 hours for their code to compile, you have FPGA. You have implicit data movement by default, but good scheduling using buffer accessor concept. I really like it. But if you don't like it because you find it really verbose, you can just use USM and just do the good old meme copy. You have pretty good interop with other programming model. I didn't show it here for the time, but you can do, for example, interop OpenMP and Sycl. We have a few apps who are doing that, and it worked pretty well. So yeah, for example, as I said before, OpenMP, Sycl, and then 1MKL, OpenMP, Sycl, and then parallel STL. So for example, we have a code who want to do a sort. In OpenMP, it's hard to do a sort on the GPU. You need to implement yourself. I know every CS person in the world really like to implement sort. It's like a rite of passage or something like that, but parallel STL will be faster than you in most of the case. So you can do that. You can use OpenMP to interrupt to Sycl to use parallel STL. The performance seems pretty compatible. I think one of the advantage maybe to compare to OpenMP is that Sycl is far simpler for the implementer to do. OpenMP is really, really complicated. The more OpenMP you do, the more complicated you realize it is. And it is a challenge to implement OpenMP efficiently. A lot of effort are put in OpenMP, so we are closing the gap and we are improving a lot, but it is the way it is, where Sycl is really more, how can I say? It was developed by implementer, so we try to put on this stuff inside. We are not too hard to implement and portable. Lot of good resources. My favorite one is just the spec. So just click on the spec and you read the spec. It's not too bad. You have a reference guide with a little, cheat sheet that you can have near your bed when you don't know how to sleep and to learn. We have this training that we'll use in 5 minutes just to show you how it works, that it works. Some people write some really nice tutorial. You have some books also for the Fortran programmer who like books. You have a books here, which is pretty nice. And you have Sycl text, which is kind of the hub where you can have everything. Do you have any question before we do a little quick, fast hands-on and how to do that? And don't hesitate to do on the Slack. And let me, I need to, I have screen sharing. I need to share new share and I need to share my full desktop. Share, perfect. Here, boom, 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 boom. So I think I keyed in the Slack, in the slide, the repo we use, and I think it will be also in the GitHub, in the big Git. I just, in my fork, I just add some README and some in presentation. You will find the slide. If you go in presentation 2022, it is not here, but it should be. Oh yeah, I didn't git pull. And I cannot git pull because I'm not at a GPU and I forgot to submit my work with no internet access. But if you git clone from scratch, you will see 2022 repo. And then you go in Sycl train and 9 Sycl of hell. It is the best name. I don't know if it is the best tutorial, but at least it is the best name. And inside you will have a lot of repo. And if you look at the README, they tell you to do module use this module file, a little long, but it is in the README. Then you can just do module load dpc++, and then you can just do make. And we'll just run the first one, or we'll run two because of time constraint, but at least you can use it. The warning, as usual, don't care about warning. And I will stop here. And teeny Sycl info. And you see what we discussed before between platform and device. So here I have two platforms. I have this NVIDIA CUDA backend, NVIDIA Corporation 1.4, and I have one device into it. And then I have another platform with the Sycl platform. And this thing is not a GPUs. This thing is a fallback mechanism. So if you run somewhere who have no CPU, no GPU, some implementation give you a fallback mechanism where you can run. Performance may need not be terrible, but you can still run. So if we look at my teeny Sycl info, it's just to show you that it is really a C++. So you see, I create a platform, it return a vector, I can loop over this vector, then I can get some information by specializing the template of get info. If you're really C++ guru, one day you can tell me, oh, can I replace, if I don't want to copy paste get info, how can I create a loop? So that means how can I store type inside, inside an array? I'm not smart enough to figure out how to do it. But really C++, and after from the platform, you can get the device, and after same thing, and you can ask some information. So really C++ and nice, pretty terse. Then you see if I run, I have that. Then we can try to make a for buffer. So this one is a copy with a buffer. Bin for buffer. That's CPP. Vim, if not, it will not work. Buffer.cpp. So here it's the example I showed you before. So I have a vector of A, global range. I read global range as asked preview in Slack. I read it directly from the std in. So I read the global range, and then I create my buffer, and then I submit. Then I create an accessor to say it is read-only. And then I access it, and at the end of the scope of my buffer, everything will be synchronized, and I can initialize, and it works. As we saw, if I do for buffer -g5, I have indeed in 2, 3, 4, 5. So everything worked as expected, as we showed you before. And I have the same example with buffer USM. Buffer is USM is stupid. I should have just called it USM because we don't use any buffer. And you see here, the code is maybe shorter because we don't need, so we create malloc shared. Malloc shared, it is blocking, so you don't need to wait. This thing doesn't return an event, it returns a pointer. So it is blocking, you allocate your thing, it is allocated. Then you create a parallel for, you don't need to do anything except synchronizing, because if you don't synchronize, this thing will be garbage. And yeah, that's it. So terser, less code, but everything. And maybe then if you use event, it is a thing where I have two kernel and I want to synchronize two kernel. And either I need to use in order queue, but here I will use event to maximize, to minimize the overhead of the scheduling. So I submit this little kernel who prints something. It gives me back an event. And then when I submit the other kernel, I just do depend event on. So I need to know that this guy need to be scheduled after this guy, because this is what I want. So I put here depend on 0. And then at the end, I need to do e1.wait because I will use e1, but I'm smart because I want the profiling, and I know if I use the profiling, it will synchronize. So I don't need to synchronize because it is implicit here. Get profiling info will give you the time the kernel took, and it will synchronize for you. So you see, when we use buffer, if you want to write this guy with buffer, you will not need to put a depender on here. What you will do is, and no event 2, you will just create a buffer. You create a buffer A, and after here, you create an accessor inside. Accessor, you will say write, and after you will use it. And after here, you will do accessor write, same thing, right? You create the same accessor using the same buffer. Buffer A, buffer A, write only, write only, write only. So they know because, oh, write only, and because you know that because we are writing on this, and I lost my my node after 1 hour. So if you load this guy, you will know that you will have a synchronization. Right? I mean, it will synchronize for you because you write, and after write, that means the runtime understands that you cannot run them in parallel. You need to have some dependency between them. So they will put the dependency for you. Where if you put to read, let's say I create a buffer and my kernel reads this buffer. So in my accessor, I say I want to read this buffer. The runtime understands that concurrent read are okay. So they will, in theory, they will execute, they will schedule both of your kernel in a way that may allow concurrency if you have room on the GPU and this kind of thing. And I think we are just 4 p.m. So perfect. It is the top of the hour, and I think it was my thing, 45 minutes. So don't hesitate to write on Slack. I hope I reply to Shen Wang on the MPI for the this. Yeah, I will need to do more research because it's a little tricky. I think my favorite way is using the functor because I think you cannot pass this, but Nevin is here, and Nevin is in the C++ committee, so he knows everything about Lambda, where me, I'm scared about Lambda. If I couple D++ with MPI, how should I know the exact number of devices using in my code? Yeah, so you see C++ guy showing up. So yeah, it's a good question how to interface MPI and DP C++. And it is exactly how the same how you interface MPI in OpenMP. When you are interfacing MPI in OpenMP, you ask your question, how many devices should my rank see? So either from the outside, the MPI will decide for you that each rank will see a different GPUs. So for your process, for your rank, you will see only one GPUs and you're good. Or maybe your MPI doesn't do anything, and then each MPI rank will see the full GPU. For example, I have 2 GPU on my node. Each rank will see 2 GPU of your node. And the famous trick is to use your rank ID, and you do modulo the number of GPU. So platform get device ID. And you are good if you do that. So both regular, nothing special. So yeah, either MPI will do it for you, and MPI will show you only one GPUs, or MPI will show you all the GPU, and you will handle how you want to split manually. So regular thing as in OpenMP and or in other vendor. I saw some people typing. Yes, I have some example for functor. If we go in Sycl train, 9 Sycl of L, advanced Inferno, 0 power for functor. And you see this one, so you just create a class where you overrode the parenthesis, and then inside the thing you can just parallel for kernel, and you have access to everything. So when you create your kernel, you can pass this, and after you can do a copy to populate everything here, to do a dig copy or whatever you want for all the seeing your interests in this, and after you just call it here, at least. But Nevin, Nevin can give you the best C++, but this is what I do most of the time. If I need to pass something, I just create a little functor. Oh yeah, template parameter type. Yeah, you're right. I think I can create some tuple and some variadic template and after extract everything. Yeah, that may work. It would need to know a compile time. I think we are screwed for runtime, or we need maybe a map of all the different type or whatever. It's not being complicated, but yeah, this is sometimes C++ is a hard issue. I can try that. It's a good idea. I may do write a little proof of concept. And I think it's the end of the talk, Roy. Sorry. So yeah, I will monitor the Slack, and don't hesitate to send me any email, anything. And for the arts question, just Nevin, not me, please.
Right on time.